Hello and good afternoon, everyone. Myself, Govin Sharma, and today I am here to present you on the topic molecular computers and Turing machines. So let's begin with the introduction. Molecular computing involves using molecules as basic computational elements. These molecules, such as DNA, proteins, or other biological components, can perform computations through interactions that mimic computational processes seen in traditional computers. Turing machines, on the other hand, are theoretical models of computation that define the concept of algorithms and computability. The scope of Turing machine involves computability. What is a Turing machine? Turing machines are fundamental abstract mathematical models that represent a theoretical concept of computational device. Proposed by Alan Turing in the 1930s, these machines serve as a fundamental basis for understanding the concept of computation and computability. The basic concept involves several key components, such as tape. A Turing machine operates on an infinite tape divided into cells. Each cell can hold a symbol from a finite set of symbols, including blank spaces. Head. The machine has a read-write head that can read the symbol on the current cell, write a symbol onto the cell, or move left or right along the tape. State register. The machine has a finite set of internal states. It can be in one state at a time, and based on the current state and the symbol read from the tape, it performs specific actions such as writing a symbol, moving the head, or changing its internal state. Transition function. This function dictates the machine's behavior. It defines what actions the machine should take, write a symbol, move the head, change state, based on the current state and the symbol being read from the tape. Turing machine operations. The operation of a Turing machine follows these steps. At any given moment, the machine is in a particular state reading a symbol from the tape. Based on the current state and the symbol read, the machine consults the transition function to determine what action to take. It writes a symbol onto the current cell, moves the left or right, transitions to a new state based on the rules defined by the transition function. The process continues sequentially, following the transition rules until it reaches a specified halting state condition. Turing machines serve as a theoretical model for computation, demonstrating the concept of algorithm processes. They can simulate any algorithm or computation that can be described in a step-by-step manner, helping to define the limits of what is computable and what isn't. This theoretical construct laid the foundation for understanding computability, complexity theory, and the capabilities of computers. Turing machine variants. Variants of Turing machine expand upon the basic model proposed by Alan Turing and introduce different capabilities or modifications to the original concept. Here are a few notable variations. Multi-tape Turing machines. These machines have multiple tapes instead of a single one. Each tape has its own read-write head. The tapes operate independently but can communicate with each other by moving or copying symbols from one tape to another. Multi-tape Turing machines can potentially perform certain computations more efficiently than single-tape machines by allowing simultaneous operation on different tapes. Non-deterministic Turing machines (NTMs). Unlike deterministic machines, NTMs can have multiple possible next actions from a given state and symbol. NTMs can explore multiple computation paths simultaneously. This non-deterministic this non-determinism enables them to potentially solve some problems more efficiently or in fewer steps than deterministic machines. Non-deterministic Turing machines are important in theoretical computer science for exploring the concept of computational complexity and understanding the boundaries of what can be computed efficiently. Universal Turing Machine (UTMs). UTMs are theoretical machines capable of simulating any other Turing machine. They can take the description of any Turing machine as input on their tapes and simulate the behavior of that machine, effectively functioning as a universal programmable computer. UTMs are significant in the theory of computation as they demonstrate what a single machine with fixed set of instructions can emulate any other Turing machine, highlighting the concept of computational universality. Each variation extends or modifies the capabilities of the original Turing machine model, offering insights into computational theory and helping explore the boundaries of computation. These variations have been instrumental in understanding computability, complexity theory, and the limits what can be effectively computed by theoretical models. Now we will talk about the limitations of Turing machines. Turing halting problems fundamental concept in computer science and logic proposed by Alan Turing. It states that there is no algorithm that can determine for any arbitrary program an input where that program will eventually halt or terminate or run indefinitely. In simpler terms, it results that there is no general method to predict if a given program will stop executing or continue indefinitely for possible inputs. This theorem has profound implications. Indecidability. Turing's proof shows that there cannot exist a general algorithm that solves the halting problem for all cases. No algorithm can universally predict whether any arbitrary program will halt or continue running forever. Limits of computation. This theorem demonstrates the inherent limitation of computation. It suggests that there are problems that cannot be solved by any other computer or algorithm due to their indecidable nature. Theoretical foundations. The halting problem is foundational in theoretical computation science, serve as serving as a basis for understanding the concept of computability, complexity, and the boundaries of what can be achieved algorithmically. The Church-Turing thesis, proposed independently by Alonzo Church and Alan Turing, is a hypothesis about the nature of computation. It suggests that any function that is algorithmically computing can be computed by a Turing machine or equivalently by any algorithmically equivalent model of computation. Key points about the Church-Turing thesis. Number one, computational equivalence. It implies that any effectively calculated function is computable by Turing machine and vice versa. If a problem can be solved by an algorithm, it can be solved by a Turing machine and conversely. Second, theoretical foundation. The thesis provides the theoretical foundation for what the idea of algorithmic computation, suggesting that any reasonable model of computation will be equivalent in terms of computational power of a Turing machine. The Church-Turing thesis is not proven formally, but he gained widespread acceptance due to the absence of any counterexamples and its consistency with observations in computation. It serves as a guiding principle in the study of computability theory, demonstrating the theoretical limits and capabilities of computational systems. Now we will talk about the molecular computers. Molecular computers are computational devices that utilize molecules and molecular scale components to perform computation. These computers harness the unique properties of molecules such as DNA, proteins, or even the individual atoms to store, process, and manipulate information. Molecular computers differ from traditional computers in several key ways, such as substrate and components. Molecular computers use molecular or molecular scale components as their building blocks, whereas traditional computers use electronic components such as transistors, capacitors, and wires. Computation mechanism. Molecular computers perform computation based on molecular interactions, biochemical reactions, or manipulation of molecular states, whereas traditional computers rely on electrical circuits and logical operations. There are some more several key ways that differ molecular computers from traditional computers, such as parallelism and density, scalability, etc. Potential advantages of molecular computer includes massive parallelism, information density, biocompatibility, and novel applications, and lower power consumption. Basics of molecular computing. Molecules, particularly DNA molecules, have been explored as potential data carriers due to their unique properties that allow them to store and encode information. DNA in particular possesses characteristics that make it suitable for data storage. To encode information into DNA, data is converted into sequence of nucleotides using a coding scheme. Each nucleotides A, G, C, T represents a binary digit 0 or 1. By synthesizing DNA strands according to this code, information can be stored and later read by sequencing the DNA. Analogy for molecular computing. Imagine a complex maze made of interconnected plates. Each pipe can carry different type of liquid. Gates along the pipes can control the flow of these liquids, directing them to different channels based on their properties. The movement, interaction, and processing of these liquids through the maze represent the computation happening in a molecular computing systems. Just like in a maze where liquid move through interconnected paths, in molecular computing, information encoded in molecules travel through specific channels and undergoes various interactions. These analogy capture the essence of how molecules could act as carriers of information and perform computation in a molecular computing environment. Molecular computing approaches. Molecular computing explores various approaches that leverage molecules and their properties for computation. Two prominent approaches are DNA computing and chemical reaction networks. DNA computing. DNA computing works on the concept of DNA computing using DNA strands as information carriers and performs computation through DNA-based reaction and manipulation. Principle in DNA computing includes DNA strand represent data and biochemical reactions such as DNA hybridization and enzymatic reaction are used to perform computation. Chemical reaction networks, also known as CRNs. The basic concept is CRN module computation using chemical reaction among molecules in a network structure. Principles include chemical reactions, which are often instructed as computation operations, take place among molecules following predefined rules, including to emergent behaviors that mimic computation. Examples include molecular encoders, decoders, and pattern formation. Real-world examples of molecular computing applications are still largely experimental and research spaces due to the complexity and challenges involved. However, some promising developments and applications include biosensing and diagnostics, drug delivery and targeting, molecular robotics. Advantages of molecular computers includes massive parallelism and energy efficiency. Benefit of massive parallelism is molecular computing systems can execute operations in parallel due to the nature of molecular interactions, allowing for the simultaneous processing of multiple tasks. Impact. This capability can significantly speed up computations for certain programs that benefit from parallel processing, potentially outperforming traditional sequential performing in electronic computers. Benefit of energy efficiency include molecular systems may operate with lower energy requirements compared to traditional electronic devices. Impact. Reduced energy consumption could lead to more sustainable computing solutions and potentially contribute to environmentally friendly technologies. Challenges of molecular computing. Computing faces several challenges that includes its particular implementation despite its promising potential. Some of the key challenges include error rate, scalability, practical implementation. Error rate challenge. Molecular systems, especially DNA-based computing, are prone to errors during information storage, manipulation, and retrieval due to factors like mutations, chemical regression, or unintended interactions. Scalability challenges include scaling molecular computing systems to handle larger and more complex computations poses significant challenges. Ensuring consistency, precision, and reliability at larger scale is difficult. Challenges in practical implementation include translating theoretical concepts and experimental demonstration of molecular computing into practical, reliable, and cost-effective systems is a considerable challenge. Turing machine versus molecular computers. On the basis of computational power, Turing machine. These abstract models of computation are highly versatile and theoretically powerful. They serve as a fundamental basis for understanding computability and algorithmic process. While they have the theoretical limitations, they can solve a wide range of problems within their computational scope. On the other hand, computing, especially DNA-based system, has the potential for massive parallelism due to the nature of multiple interactions. This parallelism can offer computational power for specific tasks that benefit from simultaneous operation. However, The molecular computers might face challenges in handling complex computation due to issues like error rates and scalability limitation. Operations. Operations in Turing machine involve reading, writing, and moving along on infinite tape. They execute computation through a sequence of discrete steps dictated by a transition function. Molecular computing utilizes molecular interactions, biochemical reactions, or chemical reactions to perform computations. Operations include manipulating molecules such as DNA strands and processing information encoded within these molecules. Limitations of Turing machine. The limitations of Turing machine are defined by the halting problem, which states that it's impossible to determine whether a given program will halt or run indefinitely for all inputs. Additionally, their sequential nature might not efficiently handle certain problems that benefit from parallel processing. Whereas in molecular computers, limitations include high error rate in molecular operation, scalability, challenges in handling larger and more complex computations, and difficulties in practical implementation due to technological hurdles. Turing machine in molecular computing. Turing machines serve as a fundamental theoretical model for designing and analyzing algorithms, including those in the domain of molecular computing. Despite the differences in their underlying mechanism, Turing machines play a crucial role in guiding the design and analysis of molecular algorithms in several ways, such as algorithm framework, computational boundaries, complexity analysis, problem-solving paradigms, verification and validation, and development of new models. Molecular, molecular computers in theory of computation. Molecular computers offer a unique approach to computation by leveraging the properties and interactions of molecules, such as DNA, proteins, or chemical reactions. Their existence and potential capabilities expand the boundaries of computational theory in several ways, such as novel computational substrates, massive parallelism, information density, biological and computer computing, exploration of non-traditional computing models, challenges, assumptions, and limits, and open doors to unconventional problem solving. So hereby we come to the conclusion. By understanding both Turing machines and molecular computers, researchers gain a broader perspective on computation. They grasp the fundamental principles of computation through the lens of Turing machine while exploring the potential of alternative computational models offered by molecular computers. This comprehensive understanding enables the exploration of diverse computational substrates, fosters innovations, and drives advancement in both theoretical and applied subjects of computation. Thank you for listening all this presentation. And if you have any doubts, you can contact me. Thank you.